Am I audible to everybody?
Yes.
Yes. Yeah. I welcome you all for another exciting
Wait a
session.
minute. The speakers are not here.
Yeah. Okay. Maybe we will wait for 5 more minutes.
Hope the speaker know that it is Singapore time.
Tanmay is here.
Yeah.
Actually, it's
Do we start with Professor Tanmay Dutta?
No, shouldn't change. Let's wait.
Okay.
Prof. Prasanta Kumar. Yeah, he's here.
Okay. Great. Yeah, so welcome to another exciting session of Magnetic Symposium 2022. So in this session, we will be having 2 keynote talks, 3 students talks, and 1 invited talk. So without wasting any time, let's start. So first keynote talk is by Professor Prasanta Kumar Muduli from IIT Madras. Topic of this keynote talk is study of spin to charge conversion using non-local spin wall devices. Professor Prasanta Kumar, you can start now.
Your audio is not visible. Not. Still, we cannot hear you.
We cannot hear you.
Maybe remove your mic and use directly your computer's mic.
Hello, can now everybody hear me?
It's better now.
But I cannot hear you actually.
Can you hear me now? Yeah, we can hear you.
Oh, okay, now you can hear me. Okay, I can also hear you. Okay, thank you. Sorry for this thing. I should have done before. Okay. Okay, so thank you very much for this introduction. And so today, so I am Prasanta Muduli. So I am a new assistant professor in IIT Madras. And today I'm going to talk about study of spin charge conversion using non-local spin valve devices. And most of this work that I will present today was actually done when I was at University of Tokyo working with Professor Washichika Otani at ISSP and University of Tokyo. So the outline of my presentation is like this. I will cover 5 different topics. And this talk is primarily designed for the students who are kind of very new to this kind of research, and also those people who are not aware of this non-local spin valve kind of research. And for the experts in the audience, I would like to apologize that many of the things that I will say will be very, very trivial. Okay, so the first I will start with a spin current and how the little bit of history about non-local spin valve devices. And the second topic I will talk about different kind of spin charge conversion processes and introduce a new experimental technique. We call it spin absorption method. And then I will give one example of a spin Hall effect study in manganese in while semi-metal, and also another example study of Rasmussen effect in bismuth oxide copper interface using non-local spin valve devices. So let me start from the beginning. So you know that the electron have a charge and also have an intrinsic angular momentum, which we call it as spin. So accordingly, we can have a two kinds of current. One is the charge current, which is sum of the spin current due to upspin and current due to downspin. And we can also define a spin current, which is the difference between upspin minus the downspin. So there can be three different possibilities. Suppose you have equal number of upspin and downspin electrons, and they are traveling towards the right-hand side. Then in this case, you can see that there is non-zero charge current, but the spin current is zero. But you might have a situation in which have an unequal number of upspin and downspin, and both of them are traveling towards the right-hand side. So in this case, you will have a non-zero charge current and also non-zero spin current. And this kind of current we call a spin polarized current. But there can be a third interesting case in which we have equal number of upspin and downspin, but upspins are traveling towards the right-hand side and downspins are traveling towards the left-hand side. And so in this case, actually, the charge current is zero, but the spin current is non-zero. And this kind of current is called pure spin current. And people are kind of very much interested to study this kind of pure spin current devices, because you can have a reduced joule heating if you make a circuit with pure spin current. Also have a very negligible overshoot fields from pure spin current. So there has been a dream for spintronics community to make a circuit with a all spin logic device using completely from spin current, so that you can switch the magnets with your spin current and create a logic device. So these are some of the theoretical proposals early on. And also people are trying to understand a field effect transistor, which will be based on spin current instead of a charge current, where you can switch on and off the spin current by using a gate voltage. So this was initially proposed in 1990s by Supriya Dutta. And these are all theoretical proposals and has never been realized at room temperature so far. And these are some of the outstanding problems in the spintronics community. So how to create a spin current? You can create spin current using a nanoscale device. We call it non-local spin valve device. And this device looks something like this over here in this picture. So you can see that there are these two blue nanowires, which are ferromagnetic nanowires. And there is a non-magnetic nanowire bridging between these two ferromagnetic nanowires. And so this kind of device are usually made using electron beam lithography using 3 different steps. And so let me explain how those devices work actually. Suppose you take one of this non-local spin valve device and apply a voltage between this ferromagnet and the copper, then you will inject spin polarized current into this copper, and due to which you will create a electrochemical potential of the copper will be splitted like shown in this picture over here, and due to which there will be non-equilibrium spin accumulation just below this injector electrode. And this non-equilibrium spin accumulation will diffuse across this copper channel, and this diffusion process will create a current, and we call it the spin current, which is the gradient of the electrochemical potential along this x direction over here. And accordingly, we can also define a spin voltage, which is the difference between the electrochemical potential normalized to the electronic charge. And similar to electrical current voltage, we can also define a resistance. We call it spin resistance, which is depends on the spin diffusion length and resistivity of the material, spin polarization, and area cross section of this spin transport signal. So now in this device, if you put a voltmeter and the other end between the ferromagnet and the copper, you can detect a voltage. And note that this voltage does not appear because of the charge current flowing in this over here, because charge current is flowing only in this closed circuit over here, and there is no charge current flowing towards this side. So this voltage appears, you can understand like this. Here you apply a voltage and produce a non-equilibrium spin accumulation below the injector. So now there is a non-equilibrium spin accumulation below the injector here. So it will produce a voltage due to the reverse process. And also you can define resistance by normalizing the voltage to the injector current, and we call it as the non-local resistance. So now if these two ferromagnets are parallel, so you will get a positive non-local resistance. And when these two ferromagnets are anti-parallel, then you will get a negative non-local resistance. And the difference between these two resistance, we call it the spin signal. So this kind of devices can be used to measure spin diffusion length of a material. So note that spin diffusion length is the length up to which spin current can travel inside the material. So here you can see that you can make a non-local spin valve device, and suppose the distance between injector and detector is d, and you measure spin signal, it would look something like this. And now if you increase the distance between these two, then your spin signal will be reduced. And so you can make many devices and measure the spin signal as a function of distance. And you can see that this spin signal decays exponentially following this relation over here. And by doing exponential fit, you can determine the spin diffusion length of your material. For example, this is the data for a copper that I measured at 10 Kelvin to be around 1100 nanometers. So now let me say a little bit about the history of this non-local spin valve device, how it was discovered, and what is the present status of this area. As we know, the spintronics has 5 different steps. One is you have to create the spin current, inject spin current, transport the spin current, and control during the transport, and at the end detect. So the creation is very simple. As I said, you can pass a current inside a ferromagnet, you can create a charge current along with a spin current, but the most difficult part is the injection. Actually, the first injection of spin current from a ferromagnet into a non-magnetic metal was discovered in 1985 by Johnson and Silsby. So what they did is they took a piece of aluminum, and it is a micron scale device, quite a big device actually, 100 micron wide and 50 micrometer thick, and to put ferromagnetic electrodes on top of it and measure these non-local devices. And they found that when these two ferromagnets are parallel, they have a positive resistance, positive non-local voltage, and when they are anti-parallel, they have a negative non-local voltage. Actually, this was the first non-local spin valve device that was fabricated. But this device was working at a very low temperature, at 27 Kelvin. So people were not much interested in this kind of thing because it didn't work at room temperature. And the first breakthrough happened in the year 2001, when Bart Van Wij's group, they could show that they could inject spin current at room temperature into copper using permalloy electrodes, and they could also transport spin current and detect, and they could estimate spin diffusion length to be around 350 nanometer at room temperature. So after that, actually, there is another breakthrough happened in the year 2007 when in Otani group where I was working. So you could show that using non-local spin valve devices, you can measure the spin hall angle of platinum at room temperature. And further detail about this experiment, I will talk in the later on slides of this talk over here. But there are also some more other important things that happen. In the year 2009, and Saroj Das could show that it is also possible to inject spin current into semiconductor silicon at room temperature. And later on also in the year 2013, people could inject spin current into a superconducting aluminum, and they could see the spin transport inside a superconducting aluminum. And another big discovery happened in the year 2007, again in the Bart Van Wij's group. And in this case, they used the graphene as the spin transport channel instead of a metallic spin transport channel. And they could show spin transport in graphene at room temperature and non-local detection. So present, actually, most of these devices are basically based on graphene because graphene has the longest spin diffusion length among all the materials. And the present record is for around 13.6 micrometer using CVD graphenes. And in fact, people can see up to spin signal up to 45 micrometers. So most of the present generation non-local spin valve devices are using graphene as a spin transport channel. And these are some of the results. So I will not go into details of this result because this was actually introduced yesterday by Amit. So I will go to the next topic now. So I will introduce some other methods where you can create spin charge. You can charge current to spin current. And then I will come to a new experimental technique, spin absorption method. So what is spin Hall effect? So I think most of the people here in the spintronics community might already know, and this is just for the students. And so spin Hall effect was actually theoretically proposed in 1969 by Diakonov and Perel, but it was a very difficult experiment. It took almost 35 years, and it was experimentally detected in the year 2004. So this effect is like this. Suppose you take a heavy metal for platinum or tungsten and pass a charge current through this material, then there will be spin accumulation on the surface. It's shown by this blue arrows over here. And this will produce a spin current, which magnitude will be given by this expression over here. And direction is mutually perpendicular to charge current direction and spin polarization direction. This is the direct spin Hall effect. So the inverse process is also true. Suppose you inject a spin current into a heavy metal, then you will produce a charge current whose magnitude will be given by this expression over here, and which will be mutually orthogonal to spin current direction and spin polarization direction. So these two effects are the most important effects in spintronics, because in direct spin Hall effect gives an opportunity for you to make a spin current, and inverse spin Hall effect gives a way to detect spin current. Because spin current doesn't produce any voltage, what you can do is that you can inject spin current into platinum and produce a charge current, and the charge current will produce a voltage, and you can put a voltmeter and detect spin current. So there is also another effect in which you can detect some produced spin charge current to spin current, and we call it the Rasba effect. So suppose you have a two-dimensional electron gas, the Hamiltonian will be some very simple p square by 2m, and the dispersion will be a parabolic dispersion. These are spin degenerate dispersion. Now, if you have if there is a special inversion symmetry is broken by at the interface of the surface, then you have the additional Rasba term, where alpha is the Rasba parameter. And now in this case, your dispersion will have a momentum dependent splitting, and this spin degenerate bands will split along the momentum axis like over this over here. So now if you take at the Fermi level, the cross section, then you will get two contours. So you can see that the inner contour, the spin is locked to its momentum and is a anti-clockwise helicity, and the outer contour has a spin is also locked to the momentum and a clockwise helicity. And actually it was realized in 1919 by Edelstein that this kind of spin momentum locking can be used to produce charge current to spin current. And in fact, it was very recently realized in the year 2013 by Rosa Sanchez. Actually, he is one of the speakers in the afternoon session today. That using bismuth and silver interface, that actually Rasba interface can be used from charge current to spin current conversion. So how does this conversion happens? So if you see this two contours, and if you apply a charge current parallel to this along the negative x-axis over here, then the Fermi contours will be shifted like over this over here, and this shifting of this Fermi contour will produce a net spin accumulation, which will be a spin polarization along this y direction over here. And now if you connect a metal, 3D metal to this interface, then it can produce a 3D charge spin current, which will be injected perpendicular towards you. And this magnitude of the spin current will be given by this expression over here, where Q is the spin charge conversion efficiency. And doing a little bit of math, you can show that this Q depends on the Rasba parameter and Fermi velocity and a time scale, which is the spin transmission time across the interface. So if you do a little bit of dimensional analysis, you can see that this charge current is a two-dimensional current and the spin current is a three-dimensional current. So this Q has a dimension of 1 over length. So now the reverse process is also true. This is called inverse Rasba-Edelstein effect. So suppose you have a Rasba interface with a Fermi contour like this, and if you inject spin current to this kind of surface with spin polarization along the y-axis, suppose, then this Fermi contour will be shifted like this over here, and shifting of this Fermi contour will produce a charge current. And this 2D charge current will be given by this expression over here, where lambda is called the Rasba-Edelstein length. And by doing a little bit of math, you can show that this lambda depends on the spin relaxation time, and the spin relaxation time of outer equilibrium spin and Rasba parameter, which you can also write as like this over here. So here also you can do a little bit of math and show that this lambda has also a unit of length. So now I will explain how you can use non-local spin Hall devices to study spin Hall effect and Rasba-Edelstein effect. So as I said, if you have a non-local spin Hall device and you measure spin signal, it will look something like this over here. And now if you put a spin Hall material or Rasba-Edelstein material in the middle, then you measure the spin signal again, then you will see that the spin signal will be reduced. And this is because some of the spin current will be absorbed by the spin Hall material. And this reduction of signal, if you know the ratio between these two signals, you can determine the spin resistance of your spin Hall material. And if you already know the resistivity of your spin Hall material and dimensions of this nanowire, you can determine the spin diffusion length of your spin Hall material. So this is a very useful technique to measure spin diffusion length of a material, which is a very tiny spin diffusion length. And now, as I said, some of the spin current got absorbed by the spin Hall material. If you put a voltmeter across the spin Hall material, then you can detect a voltage due to inverse spin Hall effect. But you will not detect voltage in all conditions, because the spin current, charge current, and the spin polarization direction are mutually orthogonal to each other. So you will detect voltage only when the spin polarization direction is shown by this yellow arrow, and other conditions you will not. And you can control the spin polarization direction by controlling the magnetization direction of this ferromagnetic electrode. And now suppose you apply large magnetic field along this x-axis over here, and you saturate your ferromagnet to along this x-axis, then spin polarization will have a direction shown by this yellow arrow. And this will, now you will get a finite inverse spin Hall resistance over here. And now if you reduce the magnetic field to 0, then this, because this is a nanowire, the magnetization of this nanowire will be aligned along this y-axis. So in this condition, you will not get any voltage by this spin charge conversion process, So you will get a 0 voltage for inverse pinhole resistance. Now, if you go to the reverse side, you will get the same thing. Now, difference between these two resistance we call as the inverse pinhole signal. And if you know the inverse pinhole signal, you can determine pinhole angle using this equation over here. Usually, we also measure the AMR of this permalloy nanowire and superimpose onto the pinhole signal to confirm that we are actually changing the spin polarization direction of the ferromagnet, and they actually match with your inverse pinhole signal. Actually, this device is also very useful because same device can be used to measure direct spin Hall effect. So what in this case, what you will do is that you pass charge current through your spin Hall material and produce a spin current inside this copper channel, and which you can detect non-locally by putting a voltmeter between this ferromagnet and this copper. So in this case, you will get a reverse signal. So this is the only experimental method in which you can measure direct spin Hall effect and inverse spin Hall effect in the same place at the same material. So I will show how you can some real life example of spin Hall effect measurement in manganese 13 using the spin adjustment method. So before I go to details of the spin Hall effect measurement, I would like to give little bit of an introduction about this manganese 13 material. So the manganese 13 is an antiferromagnetic material, and it has a hexagonal crystal structure. And you can think of this material like a made of stacking kagome layers, as shown by this picture over here. And if you look into one of these kagome layers, then it will look something like this. So you can see this has a 3 manganese atom and 1 tin atom as in the unit cell, as shown by this yellow shaded area. Now, if you look into 3 manganese atoms, the spins of these manganese atoms are at 120 degrees with respect to each other. And so this kind of spin structure is called inverse triangular spin structure. And so since this is a non-collinear antiferromagnet, usually we would expect that magnetic moment to be 0, but experimentally people find very, very tiny magnetic moment, 0.002 Bohr magneton per manganese atom, which is almost close to 0. Actually, this manganese 13 material was discovered in the Satoru Nakasuji group at University of Tokyo, where actually I was also working. So what we found was that although this is antiferromagnet and almost negligible magnetic moment, it shows large anomalous Hall effect, large anomalous Notch effect, and large magnet-optical Kerr effect. So this was a bit surprising because all these effects are only observed in ferromagnets. Nobody has seen this effect in antiferromagnet. So we were very curious what is the reason for this kind of large transverse transport effect. So we did some angle laser photo-emission transmission spectroscopy, and we found that in the band structure of this material, there are these white points, and all this transverse transport effect can be explained by the large Berry curvature from these white points. And since this material has a large Berry curvature, so one would also expect that it will show a large spin Hall effect. So that was the main motivation to study spin Hall effect in this material. So to study spin Hall effect in this material, so I prepared spin Hall devices as I explained earlier. So this is the picture of one of the spin Hall device. So this is a non-local spin Hall device. There are 2 ferromagnets, and this purple line over here is the manganese 13 nanowire, which is 200 nanometers wide and 70 nanometer thick. So the most difficult part of this kind of experiment is to prepare nanowire of this kind of material, because most of the time this nanowires either oxidize or doesn't appear in the right stoichiometry. So the way I did this thing was to deposit manganese 13 at room temperature and arrange up to 500 degrees centigrade for 1 hour, and we could fabricate reasonable quality of manganese 13. So to confirm the quality of nanowire, we also make a small nano Hall bar just next to this device. And we measure anomalous Hall effect in this nano Hall bar, and we saw that it shows anomalous Hall effect at room temperature, and the anomalous Hall effect disappears below 150 Kelvin, which is what happens exactly in a bulk sample also. But if you measure the resistance of this nanowire as a function of temperature, then you will see it behave something like this over here. And this is the typical behavior of a slightly off stoichiometric manganese 13. People have seen this kind of behavior also in the bulk samples. So making a very good quality manganese 13 nanowire is very, very experimentally difficult. Actually, I spent almost 1 year to optimize this nanowire to get this anomalous Hall effect. So right now we know that this is slightly more reasonable quality manganese 13. So then we'll try to do some spin Hall effect experiment in this device. So as I explained earlier, in the spin adjustment method, first you measure your reference device and get the spin signal, and then you measure a spin Hall device. And if you see the measure a spin signal will be reduced because spin current got absorbed by manganese 13. And from this ratio between these 2
minutes remaining.
From the ratio between the 2 signals, you can determine the spin diffusion length. So I did the same experiment room temperature and estimate spin diffusion length to be around less than 0.75 nanometers, less than 1 nanometer. And in this case also you can do the inverse pinhole effect measurement. So as I said, if you put a voltmeter across this manganese 13, then you can detect the inverse pinhole signal, and which would look like this. And from this signal, you can also determine the spin-hole angle, which will be, which I estimated to be around 5%, which is very close to the spin-hole angle of platinum. If you use the same spin injection method, and from this also you can calculate spin-hole conductivity around 46 ohm centimeter, which is very close to theoretical predicted value of 36 to 96 ohm centimeter. As I showed, the main takeaway from this thing is that although manganese 13 was not very ideal, there was slightly offset stoichiometry. We got a very large spin-hole conductivity comparable to theoretical calculations, considering very curvature calculations. So in this kind of topological material, even if you have slightly off stoichiometry, you can get reasonably high spin-hole conductivity. So also we did the same experiment in the high quality epitaxial thin films, and we found we discovered a completely new kind of spin-hole effect. We call it magnetic spin-hole effect, and you can see this paper for further details. In the interest of time, I will not go into details. So in the last part, I will try to explain the same experiment in the RASBA interface. So that is a problem in the RASBA spin charge conversion, is that this RASBA conversion coefficients have a unit, whereas spin Hall angles are unitless. So it always comes into mind whether the spin charge conversion RASBA Edelstein effect actually follows Onsugar reciprocity relation or not. So this is the main motivation for this kind of experiment. And so we did fabricate this kind of non-local devices, and we found that if you measure the direct RASBA Edelstein effect shown by this green curve over here, and the inverse RASBA Edelstein effect shown by this blue curve over here, so you will get exactly the same magnitude of signal. So this confirms that both direct Edelstein effect and inversible Edelstein effect, although they have a different unit, still the magnitude of the signal they produce is almost equal. And if you also measure as a function of temperature, the signals are the exact same magnitude. So this confirms that Onsugar reciprocity relation also valid for RASBA Edelstein effect. So now I would like to conclude the talk. So I explained how you can use non-local spin-hole devices to study spin-hole angle in manganese 13, and also the same kind of techniques can be used to study spin charge conversion in bismuth oxide and copper RASBA Edelstein effect. And I also show that an Onsugar reciprocity relation is valid for RASBA Edelstein effect. And I would like to thank my supervisor, Osich Kautani, and collaborators, and all the lab mates for their contribution.
Thank you. Thank you, Prof. Prasanta Muduli, for comprehensive insight of non-local spin wall devices. We have time for 2 questions now, 2 or 3 questions.
Thank you, Prasanta, for the nice talk. Maybe my question is about the fundamentals. Can you describe the fundamental principle behind the spin diffusion length? What property of a material determines the spin diffusion length?
Yeah, so let me go to this slide over here. Yeah, so actually spin diffusion length is the length up to which the spin current can travel inside the material, for which we need the spin to be conserved during the transport. So we need a very low spin orbit coupling material. For example, graphene, the spin orbit coupling is very, very low, so you can travel spin current quite a large distance. Also, it should have very low hyperfine spin splitting for the spin current to be coherent. So in case of we are kind of mostly interested in metals, and we have seen this copper, silver, and aluminum. The spin diffusion length is very, very large, usually up to micron at low temperatures. And for most of the metals like gold and others, they have a large spin orbit coupling. So spin diffusion length is very, very small, less than 5 nanometers. Particularly gold, it is slightly higher, but platinum, it is around 5 nanometers. So mostly determine the spin orbit coupling strength of the materials.
Okay, thank you very much.
Do you have any other questions from audience? If no, we thank Professor Prasanta Muduli again for exciting talk. So another talk is another keynote speaker is Professor Tanmay Dutta from IIT Guwahati, who will be presenting ferrimagnets in Skyrmonic world. Professor Tanmay Dutta, please.
Hi, am I audible?
Yes.
Thank you, Dr. Vijay Kumar. I will just start my video. I'm visible, right? Okay, good. Hello, everyone, and thank you.
Can you see the
Your
slide?
slides are not.
Yes,
we
I'm
cannot
sharing.
see.
I'm sharing. I'm sharing. The slides, can you see now?
Coming, yeah. Okay.
So you can see the screen now, right?
Yes, yes.
Excellent.
Okay. So hello, everyone, and thank you for this opportunity. So I have, what, 20 minutes? Is that right?
So 27
20
minutes.
27 minutes. Okay, good.
Yeah.
25
Three-
plus
three
5.
minutes. Yeah.
Okay. All right. So yeah, so my talk today is on ferrimagnets in a skyrmonic world, and it's kind of an overview about how ferrimagnets are being utilized or are being looked to be utilized in the future for skyrmonic memory or skyrmion devices. So most of this work has been done in EMPA in Switzerland, and some of this work is published, and some of this work we are still in the process of analyzing and publishing. So yeah, all thanks to all the people in EMPA. And yeah, so I would just begin today's talk with very basic things first. So we probably, most of us in this talk today are aware of what skyrmions are. These are these walls of magnetization which are stabilized recently in thin film multilayers, and before that in some crystals, before that B20 crystals, and currently they are mostly studied in thin film multilayers, and they're stabilized by something called the DMI interaction. And as you can see that this is like a schematic which shows how the magnetization in a skyrmion would look like in one type of skyrmions, for example, where the magnetization switches from up to down, but in a swirling manner. And at the device level, the application that we look forward to is to use these skyrmions in something called a racetrack memory, which was proposed like almost 2 decades back, and which would be a fast replacement of racetrack memory. And the most new and the most exciting probably or let's say proposed purpose is for neuromorphic devices, which has been theoretically already through simulations established around in 2017, but recently there has been some demonstrations of skyrmionic neuromorphic devices as well. So just a brief background on this. So around 2011, so almost a decade back, we were able to, the scientific community was able to rediscover skyrmions in a way, because skyrmions were known before this, but they were rediscovered at a smaller scale where skyrmions could be very small sizes. But they were discovered at very low temperatures of around 11 Kelvin, and sometimes they also needed very high fields and so on. So they lacked all the key points that were necessary to bring them to a device scale or to bring them to a real world device. Around 2015, 4 years from then, the scenario mostly remained the same, but there were some, there were a lot of research works, and skyrmions as small as even 3 nanometer dia could also be observed. So that kind of research was already going on at a very fundamental scale. It was only in 2015 that, later that year, we were able to see some room temperature skyrmions, which were also stable at very small magnetic fields, or in fact at zero magnetic field, by using a bias from a nickel underlayer. And the next year we saw some the skyrmions that were generated not only were small size, room temperature, and also were stable at small magnetic field. So you can see these 3 boxes were ticked in 2016. Finally, in 2017, there was a system proposed which used something called additive DMI, where 2 different kind of DMIs from 2 different interfaces. Let me get the pointer here. Yeah. So two different interfaces were used to have an additive DMI, which would allow the tunability of this kind of system. So you could use or you could build systems with different kind of skyrmion sizes, skyrmion densities, stabilize them at different fields, so that whole amount of tunability came into the picture, and they were still stable at room temperature, small in sizes, and so on. However, even then, the big concern remained about mobility, and even till today, mobility remains a concern in case of skyrmions to bring them to real world devices, which is practically scalable. So, so ferromagnets, as you all know, I mean, from ferromagnet, the journey from a ferromagnet to a skyrmion, which is a Neil skyrmion here, is mostly taken care of by these four intercompeting energies, which is exchange energy, and isotropy, magnetostatic energy, and the DMI energy, which is the most sensitive and the most critical one here. And the DMI energy actually brings in this swirling and this twisting of magnetization in the plane of the film. And in terms of the skyrmion movement, as I said, the skyrmion motion, we were able to observe like skyrmion motion, but then the skyrmion motion is only observed in current densities in the scale of 10 to the power 10, 10 to the power 11 ampere per meter square, which is quite high. And most of it is attributed to pinning, both due to defects and also because of inherent pinning in the ferromagnetic materials as well. Now, therefore, to achieve a goal of small size room temperature skyrmions, which are stable at magnetic fields and also are highly mobile and highly tunable, there has been almost a big consensus on working on ferromagnetic materials or ferromagnetic materials operating at their near compensation point, which would probably take away all the disadvantages that we were seeing in the ferromagnetic material. Now, at the device scale, if you think of a racetrack memory, as you can see here, now in a racetrack memory, the issues that were observed so far were that the skyrmions must be small. We want that, and it is difficult to obtain small skyrmions in a variety of material on only in certain kinds of materials with using probably additive DMI and all. We were able to achieve very small skyrmions, which are reproducible, and a skyrmion lattice could be observed. So that's a challenge, but by using ferromagnetic materials, hopefully we'll be able to do that. And we also see that in the next few slides that that is possible to generate small skyrmions in ferromagnetic materials. The second issue is the hindrance in high skyrmion, the mobility that I'm talking about. And it is proposed that in ferromagnetic materials, and theoretical calculations have also shown that ferromagnetic materials are better host in terms of mobility for skyrmions. And if we talk about the skyrmion Hall effect, in which the skyrmions, when they're moving, or we want them to move in a straight line, but rather they would deviate to the sides because of the skyrmion Hall effect. And therefore, they would kind of annihilate at the edges of the racetrack. And this again is proposed to be solved by antiferromagnetic materials or antiferromagnetically coupled ferromagnets, or by using ferromagnets at their or near their compensation point. The fourth thing is the distance between the skyrmions. So now in a racetrack memory, we would detect or you would encode the bits as, let's say, the presence of skyrmion as ones and the absence of skyrmions as zeros. So if we really need to detect the absence of a skyrmion, we need to be absolutely sure what is the distance between two skyrmions to be expected, and only then we know that we have missed a skyrmion, or the skyrmion is absent. Now that is not a skyrmion system is not like a hand-picked where you can pick pinpoint and generate one skyrmion at individual points as you want. So therefore, because it is random, it is not feasible to do it in this way, and therefore you will never be able to maintain fixed distance between skyrmions. So this is the problem because of which encoding into a bit in a binary device or something would not be so easy. And finally, the tunability, as I mentioned, that most of the systems developed lack tunability, and therefore you cannot make a variety of devices, or you cannot make tune it to your, or tailor it to your requirements. So these are issues, and most of the issues, as you can see, the solutions or proposed solutions are mentioned in the green. And the common theme that comes out of it is there are two common themes. One is that fermions in ferrimagnets seem to be a good idea. And the second thing is that fermions in thin film multilayers with additive DMI. So using these two common themes, we start our work ahead. So fermions in ferrimagnets have been researched in, let's say, post 2018, and some work has already been done. And in the last 3-4 years, we have seen some publications where fermions have been generated in ferrimagnetic materials at and where we have seen very low fermion Hall effect. So indeed the simulations and the theory were right, and we are able to see the effects here. And also the current densities required are also considerably lower, but not as low as we would like them to be. However, the one thing you can see here is that unlike the 2017 publication in ferromagnetic materials, where you could generate a lattice of fermions, here you can only generate, in these ferrimagnetic materials, you can only generate individual fermions, which was the case earlier when we started with ferromagnetic materials. So even in ferrimagnetic materials, we are kind of in a phase now where we are only able to generate individual fermions. But to really go ahead, we really need to generate them in bulk and at very high densities and so on in a lattice formation. So one thing to note here is that these ferrimagnetic materials that has been used are single layer ferrimagnets, and mostly multi-layers have not been used. But in our work, what we have used, as we'll see now, is multi-layers. So, okay, so just to summarize what we have discussed so far, there are two problems that we're, or let's say summarize and pick two problems from there. So we are picking two problems from what we have discussed so far. One problem is the loss at the device edges. As I mentioned, that when the fermion moves from in a direction, it kind of moves also has a lateral movement because of the fermion Hall effect, and at the device edge it gets lost. Now this is proposed to be solved in two ways, or three ways rather. So one proposition is to use ferromagnetic multilayers which are anti-ferromagnetically coupled, and therefore the fermions generated in two different ferromagnetic parts are anti-ferromagnetically coupled, and therefore they will not let each other deviate, and they will move in a straight line. So this is the work that was published by William et al. In Nature Materials in 2020. And the second solution that is proposed is what we are working on. We are working on ferrimagnetic thin films, which will generate fermions. And if we are able to operate them near their compensation point, we will be able to minimize the fermion Hall effect to the least possible, while still being able to move the fermions around in the racetrack. Now, this is one problem. The second problem is the distance between the fermions that I mentioned. And there are again different solutions that are proposed for it. So here you can see the one theory paper was that 2-lane racetrack devices. The second solution was proposed in this paper where 2-layer guided track was proposed, and the third solution was to have two different fermion states. So instead of having one fermion or one fermionic state, which is difficult to use as different kinds of bits, you can have two different fermionic states in which one can be used as a 0 and the other can be used as a 1, and therefore you will not need to take the absence of a fermion as another bit. So rather than in that case, the distance between the fermions will not be of big concern. Now this was demonstrated in 2018 in a B20 crystal, I think, of iron germanium, where they showed the existence of chiral bobbers and fermions together. So both are chiral features, and both of them can be moved around, and but one has a lower, let's say, net magnetic surface charge, the other has a higher magnetic surface charge, and therefore you can distinguish between the two when you are reading them. So and therefore they can be used to encode zeros and ones. Now this is the third solution, and we are now what I'm going to show now is a alternative solution to the same idea, but a different kind of solution to the same idea. Now okay, so I have already shown this work of 2017 in a ferromagnetic material. So on the top, this is the work on a ferromagnetic material of iron cobalt multilayer. And you can see this fermion lattice that was generated. And this is the structure that was there. So a platinum, cobalt, iron, and iridium, and this was repeated 20 times. Okay. And the two DMIs at the two different interfaces, they stabilize the fermions here. Now, in our work, we brought down the number of layers from 20 to 5. So this is the structure that we are using. We are using thicknesses of iron and cobalt at 0.3 and 0.6. And we are repeating the same layer, and we are bringing down the number of multi-layers from 20 to 5. So this is the MFM image, and you can see the skyrmion lattice, which is similar to what was observed in 2017. Now you can see all the skyrmions here seem similar. They have similar MFM contrast. Now, when we introduce a ferrimagnetic layer of 3.8 nanometer here, but we change the thickness, but that is not so important here. But if we have a ferrimagnetic layer, so the ferrimagnetic layer is a terbium, gadolinium, cobalt multi-layer, and this ferrimagnetic layer is placed between two different skyrmion layers. So the top and the bottom skyrmion layers are as similar to the one I just showed before, which was already observed in 2017. But now we have placed a ferrimagnetic layer between these two top and bottom ferromagnet skyrmion layers. And the moment we do that, we see that in some samples we don't observe anything. All the skyrmions are generated in the same MFM contrast, nothing out of the blue. Everything seems the same as before. However, in certain cases, we did observe two different contrasts. So you can see there are some very bright ones, and there are some which are less brighter. So this is two different chiral structures. You can see both of them are chiral, but they have two different intensities. And this was interesting. And this was also partly planned, but also partly accidental. And when you observe them, and this kind of gives us the tool or the platform on which we can realize what we had discussed before, that is having two different kind of chiral states. So now we can have a 0 and a 1. Probably maybe the brighter one is a 1, and the less brighter one is a 0, for example. So how is it different from what was observed in 2018 already in this paper that I showed you? So although in this paper the same logic was used, but the problem with this work was that firstly it was generated in a B20 iron germanium crystal. So it lacks all the possible device fabrication compatibility. At the same time, it was generated at a temperature of 95 Kelvin, so which is quite low and is not therefore fruitful for a real world device application. But in our case, everything was done at room temperature, and they were quite stable, fairly stable. If I show you in the next slides, they were fairly stable, and they were developed in thin film multi-layers, which is compatible with the current technology. So it can be easily scaled up and implemented into a device. Now, if we look at this, so these are processed MFM images, and if you look at these images, so we have just taken one sample for a demonstration, and if we look from the left hand side and go on to the right hand side, so the field is increasing from 0 millitesla, 94 millitesla, 133, 140, 147, all the way till 177 millitesla. So you can see that we start with these striped domains, and we end up with, or in the middle somewhere, we have both the very bright and the less bright chiral structures. And at the end, we have only the less bright chiral structures, right? So then we take only 3 skyrmions. So we choose 1, 2, and these 3 skyrmions, black, blue, and yellow. And then we try to see the evolution of the skyrmion intensity as measured by the MFM in this graph. So if you can see that when we start at 130, so let's say this 133 is being plotted here. So at 133, we'll see that out of the 3 skyrmions, the 1 skyrmion is at 0.5 hertz. So this one, so it's very less bright one. It's a light one. But there are 2 skyrmions, which are the black and the blue here, and they're very intense. And you can see the MFM contrast is 1.07 hertz. So the higher the contrast, higher is the magnetic charge there, right? So as we increase the field, you can see that the evolution of these three fermions. So at some field, we can see, for example, at this field, which is 161 at 161 millitesla, one of the very bright one switches, I should not say switches to, but let's say converts to a less bright one. So you can see here. So it converts to a less bright one. And if we increase the field further at 177, you can see even the remaining bright skyrmion also transforms into a less bright skyrmion. And at this field at 177, all the skyrmions are in the less bright state. Okay. So there is kind of a phase where there is a coexistence of more bright and less bright states. And at some point, all of them turn into less bright. And if we increase the field further, all the skyrmions will annihilate. Now, what are we observing here? So this is just an MFM observation. So we are sure we are observing two different states of skyrmion. What we are also observing is that we are observing there is a shrinking in the radius of the skyrmions, which we can say because the MFM contrast is decreasing. So the MFM contrast can be directly correlated with the shrinking of the dimension of the skyrmions. Now, how do we explain this? What is really happening here? So of course, to understand this, we had to take help from simulation. But before that, we also did some controlled experiments to really understand what is going on. And if you look at these controlled experiments and these controlled samples, you can see that when we generate a single skyrmion 5 repetition layer, we have skyrmions where the intensity is around 0.32 hertz, as you can see here. Similarly, now if we grow this on a ferrimagnetic substrate or a ferrimagnetic underlayer, we still have a similar contrast, as you can see. So it is still around 0.24, so which is very similar to this one. Now, next, when we combine these two together, so we have now 10 repetitions instead of 5. So instead of 5 repetitions of skyrmion, now we have 10 repetitions of the skyrmionic layer, that is the iron, cobalt, platinum, iridium multilayer. Now this is repeated 10 times, and you can see that the intensity kind of doubles, and we kind of now see 0.71. This is the MFM contrast. So which makes sense because the magnetic surface, the magnetic volume is increasing, or the skyrmionic volume is increasing. Now, if we replace or at the middle of this, we place a tantalum layer. So there is no ferrimagnet here. So we place a tantalum layer, and you can see that that there is a reduction in the MFM contrast, which is probably because the signals that we are getting from the bottommost iron cobalt layers is now reducing because the distance from that for the tip is increasing. So but still it's somewhere between this and this, so it's around 0.54. Now the interesting part comes here. So when we replace the tantalum with the ferrimagnet,
2 minutes remaining.
okay, thank you. We replace the tantalum with the ferrimagnet, we see that we have two different phases, right? So this is what we observed before. So we have two different phases here. One is a 0.58 hertz, one is a 1.05 hertz. Now, to explain this, as I said, we took help from simulation. And from the simulation, what we could understand was that there are two kinds of skyrmions that were generated. One was skyrmions which were generated in two different ferromagnetic layers separately, and there was nothing in between in the ferrimagnetic layer. But when we looked at, but there were the high intensity ones where the skyrmion kind of punctured through. So there was a continuity of the skyrmion in between the two ferromagnetic layers all throughout the ferrimagnet layer as well. So because of this, you can see that the intensity is much higher. Also, these kind of skyrmions are wide skyrmions where it is punching through, and they are wider. Also, they are, the magnetic volume, the skyrmionic volume is higher, and therefore they are much brighter. Now, I will just keep this because I don't have much time. I will just show that we therefore next had to address the tunability question, and we needed to see if we can tune these materials to what we like. And what we observed was, I will skip this. Okay, so what we observed was that, yes, indeed, we could tune them. And by changing the thickness of iron, which was critical here, by changing the thickness of iron in the multilayer, we could change them from a state of coexistence. Like in the middle, we have the coexistence. On the right side, where the thickness of the iron layer is the maximum, is 0.35, we only have we only have the tubular states, and at the thinner iron regime, we only have the incomplete skyrmion states. So indeed, we could control the existence of this or coexistence of the species. So we could make one species higher or one species lower by changing the iron
Last
thickness.
1
So there
minute,
was
bro.
this tunability as well. Okay, so I have some other part. Probably I will skip that because of lack of time. Yeah, so I will probably just end here by saying that in yeah. So there was one last thing that I want to show you, which is here. Okay, so in this, what we did was instead of using a iron cobalt multi-layer separated by ferrimagnets, we completely replaced the ferromagnet material of iron and cobalt with ferrimagnets. And here is the last slide, and here we could observe that we could obtain skyrmions at very small. Like we are still far from the compensation point, as you can see here, but we could reduce the skyrmion sizes. We can make them highly tunable and also generate them in ferrimagnetic multi-layers. Okay, so I will stop here. I'm sorry I could not continue further. Yeah, thanks to all my collaborators, including in EMPA and also in other institutes in Italy. Thank you. I'll stop here.
Thank you very much, Prof. Tanmay Dutta. I always find skyrmions very interesting. And thank you for detailed coverage of the skyrmion sky. Floor is open for questions.
So I have a question. Hi, Tanmay. It was a nice talk.
Thank
So
you.
the question was regarding the addressability of the skyrmions, because you have been showing like the MFM can be used in order to detect the skyrmions, right? But if you want to see them through electrically, what is the option for that?
Yeah, so MFM is only for an experimental basis for research studies and all. Of course, it cannot be used at a device scale. And probably for the device scale, what we'll need to look at is more of some resistance-based techniques, maybe EMRs, having them separated by some kind of a tunnel junction, or maybe AMRs in some case. But I think we will have to exploit different kind of change in resistances by the presence of different skyrmionic states. I think that's the only way we can.
But even the resistance state is also corresponds to skyrmions will be very,
not individual. Yeah, not individual.
Yeah.
So addressing individual skyrmion readability will always be a challenge, I think, unless you make some kind of a, how do I say, some kind of a gate where you only allow skyrmions to pass one at a time or something like that. Otherwise, individual skyrmion addressability or readability will always be a challenge.
Generating itself is a hassle.
Correct. So here, what I did not show was that in using ferrimagnets, we could actually lower down the magnetic field that we need to generate the skyrmions all the way to around 5 millitesla. Whereas if you look at the thin film multilayers in ferromagnets, a field of around 100 plus 100 to 200 millitesla is necessary to stabilize them. So we could really reduce them by 95% in ferrimagnets. So those things kind of work out well in case of ferrimagnets. But ferrimagnets, of course, have their own challenges, which, of course, I could not discuss today, but it also has its own challenges.
Yeah, just one question for the ferrimagnets, like as you mentioned, like for the ferrimagnets, there is a compensation temperature. Like, is the compensation temperature is below the room temperature, or with that we can use it as room temperature skyrmion generation in the ferrimagnetic case?
So, I mean, if the compensation point is below room temperature, then it will be a problem. But then we want to select a material such that we can work with it at room temperature. So the material we are choosing at this point, which is iron, gadolinium, cobalt, and terbium. So the different alloys of it, we can reach compensation even at room temperature. So by changing, I mean, of course, by changing.
Because even for the dominant motion, also the ferrimagnets, like we are not reaching to the room temperature in order to drive them and inject them. Yeah.
Correct. And I think the bigger challenge which today we are trying to address, I mean, not me, but my collaborators back in Switzerland, where I was working as a postdoc, they are still trying to address is the movement, because it's very easy to assume that the movement at that compensation or those kind of compositions will be smooth and everything will be fine. But the problem with ferrimagnets is that, especially with terbium, gadolinium, is that there are a lot of surface or material defects that come in. It's not a material which is free of material defects, and therefore that kind of brings in a different kind of challenge of the movement again. Although the movement is theoretically is supposed to be improved for ferrimagnets, but there are materialistic challenges or material based challenges that needs to be overcome there, and that's something that we are working on.
Thanks again
Sorry
for the
to
wonderful talk.
interrupt. Yeah. Due to lack of time, we need to move forward. Thank you again, Professor Tanmay. Yeah.
Thank you so much.
So-
Please don't address me as professor. I am doctor.
Yeah.
I'm Dr. Tanmay Dutta, so let me be addressed.
Yeah.
Thank you.
Thank
Thank you for this
Yes.
opportunity. Thank you.
Yeah. So now we have three talks from students. So let's start with the first one by Chinmay, Chandan, Parhi from VIT Vellore. The topic of talk is effect of graphene oxide on structural and magnetic properties of lead-free magneto-electrocomposite. Yeah, so Chinmay, you can start right away. Chinmay.
Hello, am I audible?
Yes. Yes.
Thank you for giving me the opportunity.
Yeah, so you have 12 minutes plus 3 minutes for question answer. Yeah, please start. Yeah.
Good morning, everyone. I'm Chinmay. I'm going to present my presentation on topic of effect of graphene oxide on structural and magnetic properties of lead-free magnetoelectric composites. I've done this under the guidance of Dr. W. Madhuri, Associate Professor, Center for Functional Material, VIT Vellore. Here are my objectives of this work: synthesis of graphene oxide, development of magnetoelectric composite for high frequency application, study the dielectric, ferroelectric, and magnetic properties of the magnetoelectric composition, and the study of effect of graphene oxide on the structural modification of microstructural, structural, and properties of composites. So basically, we need to understand what is multiferrous. Multiferrous is a solid-state compound which is having two or more ferro properties that can be ferroelectrics, ferroelastics, and ferromagnetic. Magnetoelectric composites are those composites which is having coupling between ferroelectrics and ferromagnetic counterparts. So nowadays, the focus of researchers is shifted to magnetoelectric properties because of its exhibiting functional properties for the day-to-day applications. Nowadays, there is a search for room temperature multiferrous property magnetoelectric composites, which is exhibiting magnetoelectric coupling at room temperature. In this study, we selected cobalt nickel ferrite for its higher magnetization, crystalline anisotropy constant, and which will help us to gain the more magnetization with respect to the other compositions recorded before. BZP is a ferroelectric material having high d3 value and higher polarizability compared to the lead-free counterparts. Graphene oxide is the auxiliary form of graphene, which is having a wide range of applications. It is a insulating material and provides higher tensile strength of the material. Synthesis of graphene oxide. Graphene oxide is synthesized using basically research grade graphite, sodium nitrate, H2SO4, which is tied continuously at 10 degrees Celsius. It is based on the modified Hammers method. Then we have to add some potassium permanganate. Then it is continuously stirred at 98 degrees Celsius. Then we are adding some hydrogen peroxide. After 2 hours, we are centrifuging the solution and drying it at 70 degrees to obtain the graphene oxide. To synthesize the magnetoelectric composite, cobalt nickel ferrium barium silicon and titanides are synthesized using microwave sintering. So the conventional ceramic tool. Then both these cobalt nickel ferrite and barium silicon and titanides are ball milled it at pulverized classic 6 ball mill instrument with 300 RPM for 10 hours. Then it is annealed at 800 degrees for 20 minutes. Then after the pelletization of our composition, it is gone through a microwave furnace for final sintering at 1200 degrees Celsius for 20 minutes. The results and discussion. Primarily, the synthesized graphene oxide is come from the XRD pattern of graphene oxide, which is similar to the JCPTS card number 491717. It is characterized to the Bronca D8 X-ray diffractometer. Cobalt nickel ferrite and barium silicon titanides are also both individually synthesized and characterized for the formation of proper phase. It is observed that cobalt nickel ferrite is having a cubic structural phase, whereas barium silicon titanides also having a cubic perovskite phase. From the XID of magnetoelectric composite, that is having 50% of cobalt nickel ferrite and 50% of barium silicon titanides, it can observe that both the ferroelectric and ferromagnetic counterparts are present in the semi-composite phase. So with the addition of graphene oxide in P composition, that is 0.5%, 1% and 1.5% of mass of the total composite, it is observed that the solder peaks inside the magnetoelectric composite is disappearing, whereas there is a slight shift of peaks towards the higher theta value. It might be the reason due to the hybridization of graphene oxide with respect to the magnetoelectric composite. The microstructure. From the microstructural study, we can see that our magnetoelectric composite is having one bipyramidal structure. We can clearly see from the microstructural figures that our magnetoelectric composite is having a bipyramidal structure, whereas it is also having two different phases in a material. So this confirms that there is a presence of two different phases in our magnetoelectric composite. From the index, it confirms that there is no presence of, there is absence of any secondary impurities in our composition. Same thing is observed for all the graphene oxide magnetoelectric composite with three different compositions, that is having bipyramidal polygonal structure. And the IEEE spectra of all the compositions confirm that there is no presence of any secondary or impurities in our material. To study the bond vibration of the material, we have gone for the Fourier transformation analysis. From the FTI profile, the high frequency evolution bands in the range of 449 to 601, which reveals that the composite is made up of barium silicon titanate and cobalt nickel ferrite contains only metal oxide. With the increase of graphene oxide composition, we can observe that there is a disappearance of peak gradually there is a disappearance of peak, which is evident from the XRD also, where the secondary peaks are merging and becoming the sharp peak with the increase of graphene oxide, and there is a shift. So in the profile, it reveals that patching vibration associated with OH bond, CC double bond, and CO bond FTIR, which is corresponding to 1026, 1631, and 3267 is observed for 1.5% of graphene oxide composition. the dielectric property of our material. It is observed that our material is having a high dielectric constant, that is around 40,000 dielectric constant, and which is having a dielectric relaxation around 250 to 500. Dielectric relaxations are due to the thermal agitation of our dielectric dipoles, which will result in the predominance of entropy, so that our dielectric constant reaches the maximum value. The dielectric Q temperature is observed at 445 degrees Celsius, and the loss is also the increasing with respect to the increase of frequency. The loss is decreasing with increase with the frequency. Due to that, in the higher frequency, the dipoles are not able to align itself according to the electric field, the direction of electric field. With the addition of graphene oxide into the composition, that is for 0.5, it is observed that the dielectric relaxation increases, and it is observed two different dielectric relaxation in our material. And the dielectric constant increases, whereas the dielectric Curie temperature decreases to around 520, and the diffuseness in our dielectric transition and the relaxer properties of our material increases. Same with the increase of 1% of our graphene oxide, the diffuseness increases, whereas the diffuseness and the relaxer property of our material increases, whereas dielectric constant and the Curie temperature is decreasing gradually.
2 minutes remaining.
So here is we observe that around maximum around 1,35,000 dielectric constant is observed, whereas the maximum the dielectric Curie temperature is around 325. And all these high dielectric constant and higher losses can be used exploited for the high frequency applications. To the study the ferroelectric properties, the ferroelectric loop is studied. It is observed that to increase the graphene oxide concentration in our material, the polarizability increases, whereas the perceived field is decreasing. To study the magnetic properties of our material, the image curve is studied, and with the increase of graphene oxide concentration, it is observed that our perceived field is increasing gradually, whereas our saturation magnetization is decreasing for 0.5%, and again it is increasing for 1% and decreasing at 1.5%. Conclusion. So, graphene oxide modified material composite consists of cobalt nickel ferrite and branched silicon type to successfully synthesized using conventional ceramic ware method through the help of microwave sinking. XID reveals and XID SM reveals the microstructure and structural parameters of our composite. The UV spectroscopy and FTI spectroscopy studied the optical and bond stretching hallucination of our material. Dielectric properties of metal-electric composites are measured using impedance analyzer, and it is observed that with the graphene oxide doping concentration, maximum polarization value and dielectric constant increases, whereas dielectric Curie temperature and the saturation magnetization decreases. So these properties can be exploited for high frequency applications. These are some references.
Thank you, Chinmay, for the talk. Floor is open for 2 questions.
Hello, Chinmay. Hello. Thanks for the nice talk. I have a question regarding your dielectric measurement. So, have you studied any magnetodielectric study? I mean, you have any way probe that magnetodielectric measurement?
Yes, we are studying that dielectric approaches as of now.
Okay.
Hi, Chinmay. I have one question. So, for which application are you targeting for your composite magnetoelectric?
High frequency application is phase shifters and electromagnetic shielding.
Okay. And did you observe any temperature dependent response or effect in your material?
Yes, sir. Though we can see that with the increase of graphene oxide concentration, our field temperature is decreasing. And nowadays, everyone in researchers are is searching for the room temperature magnetoelectric coupling, so that with the increase of with the increase of graphene oxide into more concentration, the field temperature can reduce it around below 100 degrees, and we can exploit it to some more realistic applications in our day-to-day life.
Thank you. Yeah, so let's thank you again, Chinmay. Let's move to next talk by Amit Chauhan from IIT Madras. Topic of his talk is on exploration of novel quantum physics and large magnetic anisotropy energy in low speed D5 perovskites. Amit, you can start your talk now.
Okay, thank you. Let me share. Do I need some permission to share the screen, or?
I think you might have permission.
It is showing that your browser is preventing access to share screen.
Dr. Ramu, can you provide him
I
permission?
don't think
I think you can share.
all part. Yeah, who can share in the sense like all participant can be shared. Yeah, you can
I
share.
am when I click on share screen, it is showing your browser is preventing access to your.
It's your browser, right? So you are
Yeah, so
accessing through browser. Are
I
you
am
app?
Mozilla.
So maybe you have to change the browser in this case because the options are like enabled for everyone can actually present. I mean, share the file.
Okay. Wait. Or I will connect again. Just give me once. 10 seconds.
Yeah.
Is the next speaker also a student?
Yes.
In that case, maybe we can swap. We can ask the next student to start first.
Okay. Soumyaranjan, Ratha, are you here?
Yeah, he's
Yes,
here.
sir.
Yes.
Yeah.
Please go ahead.
Yeah. You can start.
Okay, sir. Thank you so much, sir. Is my screen visible?
Yes. So you have 12 minutes and 3 minutes for question answer. I will remind you before 2 minutes. Yeah. Thank you.
Okay, sir. Good morning, everyone. Thank you so much for the opportunity to represent my work. I am Soumyaranjan, PhD student of Akita University, Japan. I am going to present on the influence of lanthanides and cobalt substituent in the magnetic properties of bismuth ferrite multiferroic thin films. And I'm working under the supervision of Professor Satoru Yoshimura. So we know very well the importance of magnetic materials in the memory devices. For example, in the case of hard disk drive, we write data on the platter by using a coil. And in the case of STD RAM, we write data by using spin current. Just I'm going to the concepts. And in the case of newly invented restrict memory, we write data by means of spin current also. And if we think about the magneto-optical devices, for example, the spatial optical modulator, which needs Kerr effect. The Kerr effect should be highly remarkable in this case, and this also needs spin current to write data. In all the devices, we found one problem to write data. Either we need any inductive current or spin current, which really consume very high amount of energy. how can we solve this problem? How can we solve what we have to do to get rid of this problem? Okay, let me explain details about the restrict memory. I'll focus basically on this. As we know, IBM introduced restrict memory where we are going to use nano wires, and by means of a spin current, we are going to write data on the restrict memory. As we know, in the writing element, if IBM will be using the same concept as they did in the hard disk drive. That means by using the coil, we need billions of coil for the billions of nanowire, which really consumes very high amount of energy. And just imagine if in case of this coil, we can use the multiferroic film, then we can solve this problem. We'll discuss how we can solve this problem by using multiferroic film. Okay, so as we know, the polarization direction of the multiferroic layer will be controlled by electric field. The first point is that the polarization direction we can control by using our electric field. And the second point is that the magnetization direction of metallic ferromagnet layer will be controlled by magnetization of multilayer through the magnetic interaction. We don't need any coil to create magnetic field or to write data. Just by giving the polarization or by changing the direction of the polarization, we can write data on the restrict memory. So now no need to use of this coil, and we have already patent on this work. So the first important thing is that this material or the material for the multiferroic film should have a very good perpendicular anisotropy and high saturation magnetization. This is really very important for device application. Okay, so as I discussed about multiferroic thin films, we know very well these are the materials that exhibits more than one ferroic properties in same phase. Here I will be focusing on ferroelectric property and ferromagnetic property, and these are mostly perovskite structure, AbO3 type structures. Okay, so there are so many multiferrite material, but I consider bismuth ferrite. The bismuth ferrite contains iron at the center, the face contain oxygen, and the corner contain bismuth. Other features are like it has spontaneization, polarization along the diagonal. It has Curie temperature around 100 degrees Celsius, 1000 degrees Celsius, and the nil temperature is around 600 degrees Celsius. This is clear that now we don't need to worry for the temperature, because we are getting the multiferroic properties in the room temperature. But the problem with this material is that it has a G-type antiferromagnetic property, which is a problem for the device application. If we can solve this problem, then we can ask this device to be used in the magnetic devices. Okay, so we came across some papers. They are substituting few elements. For example, here there is a paper by DH1, and they are substituting barium, and you can see the signature of enhanced magnetic property as well as electric property. That means we can substitute some elements in the bismuth ferrite multiferroic thin films to enhance the magnetic property to get rid of the antiferromagnetic property. Okay, let's see how it will work. As I already discussed, by changing the polarization direction. In this case, this orange part represents our multiferroic thin film, and these are the electrodes. If I'll change the voltage direction, then the polarization direction will be changed. Accordingly, the magnetization direction will be changed. That will lead to a different bit. So we can save data by means of our multiferroic thin films in the writing elements. So it causes very low writing current, that means low electric consumption, and this is very simple. We don't need to use any noble material also, so this is very low cost. Okay, so if we think about the material fabrication, we fabricated this by using the pulse DC reactive sputtering with very high frequency plasma irradiation. Like all sputtering machine, we have also a target and substrate. We create the plasma of argon and oxygen. The high energetic argon and oxygen will hit the target, and the one atom will be detached, and it will move towards the substrate, and it will be settled down. The most important thing is that it has pulse DC reactive sputtering. As we know very well, as process goes, this plasma will be accumulated on the target, which will hinder the movement of other charged ions towards the target. But if we can use the pulse DC on for certain time, off for certain time, we can remove this arc current, and we can smooth our process. And the second important thing is that when the target atom will be moving towards the substrate, they may be undergo bombardment. But if we are allowing few atoms at a time, then off, then atom, few atoms, the first bunch of atom will be settled down on the substrate by searching its potential position, then one bunch of atom will be settled down. Like that, we can get a very good crystallization. I will show you the proof how it shows very high crystallized thin films. So this is the device which we are using. You can see here, first we substituted a barium by using our RF sputtering and pulse DC sputtering. The pulse DC sputter thin films is giving very highly enhanced magnetic property against the RF. That means the pulse DC is highly important or is really effective to enhance the magnetic property by means of crystallization. So it's measured like that, 1.5 times larger pulse DC property than RF. But the problem with this material is that it is in plane magnetic anisotropy. As we know very well, for magnetic device application, we need perpendicular magnetic anisotropy. So this is the drawback. In the second case, we substituted lanthanum in A side and cobalt in B side, but previously we substituted manganese. You can see the magnetization is not so good. Then we substituted only lanthanum. Then you can see the yellow line, still not good. But when we tried lanthanum and cobalt combination, the properties really improved. And we got our desired property, that is perpendicular magnetic anisotropy. That means not only lanthanum or not only cobalt, but also together is really effective to enhance the magnetic property. So these are the hysteresis loop and P hysteresis loop, which gives the signature of the enhanced magnetic property. So here I'm going to explain my study in two ways. First, I told I will substitute lanthanum and cobalt, but I don't know at what percentage I should get the optimum or the enhanced magnetic property. So first, I will change the cobalt concentration with different composition. I will fix at a particular point of cobalt where the magnetization is really high. Then by keeping that cobalt composition as optimum, I will substitute different lanthanoids element like lanthanum, neodymium, samarium, gadolinium, and dysprosium. Okay, let's see. So as I told, I will change cobalt composition. You can see here no cobalt. Then I increased cobalt. So when I'm increasing cobalt concentration, the properties, magnetic properties is getting enhanced. That means cobalt is really important in the B side to enhance the magnetic property. In the second case, if we think about the core effect for the magneto-optical devices, here also when I'm increasing cobalt composition, this is increasing. That means cobalt is really important, and we have estimated the value is around 25% of cobalt. So now I will be changing the A side by keeping the cobalt fixed around 25%. So actually this is a very rough discussion. We are not going into very clear discussion. As we see, this magnetic moment is getting cancelled when only lanthanum, but when we are putting cobalt, maybe some of the magnetic moment is getting depressed, so that the entire magnetic moment is not getting cancelled. We are getting some enhanced magnetic property. So this is a paper published by Professor Hiroshi Naganuma. So he substituted different B side substituent. So he got a very good magnetic property when he substituted cobalt, but this was not perpendicular anisotropy. But when we substituted lanthanum and cobalt, we got perpendicular anisotropy. That means we can say lanthanum along with cobalt is really effective to enhance the magnetic property. What's the physics behind it? To know this, in the next year we are going for the synchrotron radiation study. So I told okay. So this is the graph which shows about the neodymium substitution. You can see the neodymium substituted bismuth ferrite is showing very high remarkable magnetic property. Okay. So in the second result, I will substitute, I told already, I'll substitute different lanthanoids, and this is around a composition of 40 to 60. You can see among all the lanthanoids, when I substitute a neodymium, it's giving high magnetic property or high saturation magnetization, of course, perpendicular anisotropy. That means for my memory device, I can demand till now the neodymium substituted bismuth ferrite is essential or effective. In the second case, when I will think about the Kerr effect, you can see the lanthanum substituted bismuth ferrite is giving very good curve. That means I can say the lanthanum substituted bismuth ferrite can be used in the optical devices. Here also same, the rough discussion is like first we substituted barium, then lanthanum. You can see the lanthanum substituted curve is really remarkable, but here in the case of barium is not that much remarkable, increasing but not remarkable. So here also we are trying. Okay. So I'm skipping this and this is the summary. I'll be explaining few points in the summary. You can see I changed the lanthanum, different lanthanoids as well as cobalt. You can see the neodymium substituted is giving high MS and anisotropy. That means this is better for the memory devices. And the lanthanum substituted elements is giving high Kerr angle. So this is better for the optical devices. So this is the two most important result I'll be concluded here. In the future, we are going to try different lanthanoids or other elements and the physics behind it by the synchrotron radiation study. Thank you so much for your patience.
Thank you, Soumyaranjan. We have one time for one question only. Any questions from audience? If no, I can ask one question. So you started your talk by saying that your device design will save energy. So how much energy saving you estimate compared to IBM design?
Sorry, Professor, actually we didn't go to the estimation of energy. Now we are focusing on the material. Actually, what is happening when we are substituting different material, we are getting its pro level, means better. If we'll get the best one, then we'll go to next the energy consumption measurement.
Okay, thank you. Yeah, so Amit, are you ready now?
Yeah. Let me see.
Yeah, you can start your presentation. Yeah.
Yeah, it will work. Yeah, it's coming.
Yes.
Yes.
You can start your presentation. Yes.
Okay. My voice is coming fine.
Yes. Everything is all right. Yeah. Maybe you can use full screen if possible. Yeah. Good.
So first of all, I would like to thank the organizer for giving me such wonderful opportunity to present my work. As the title of my talk suggests, it is based on the exploration of novel quantum phases and large magnetic anisotropy energy in low spin D5 perovskites, where I will explore both the bulk as well as the ultra thin films to see what are the effects of dimensionality in these kind of systems. Here is a brief outline of my talk. First, I will give a brief overview of how the novel quantum phases emerge as the interplay of different competing interactions like Coulomb repulsion U and spin orbit coupling in the systems. So I will start first with the low spin bulk perovskite, where I will discuss the construction of model Hamiltonian and full-fledged DFT calculation to construct these phase diagram in the space of on-site Coulomb repulsion U and spin orbit coupling lambda. And after that, I will discuss the effect of structural distortion in bulk perovskites and how it affect the spin anisotropy in the system. In the last part of my talk, I will discuss how the bulk phase diagrams evolves as a function of both dimensionality and the termination effect. And then I will conclude by discussing the large magnetic anisotropy energy in the thin films and what is the underlying origin of that. So as we can see from this table, as we move down in the periodic table from 3D, 4D to 5D electrons, while the strength of Coulomb repulsion decreases drastically, the strength of spin orbit coupling increases significantly. Why? The reason is that the spin orbit coupling roughly goes as fourth power of the atomic number, and as we move down in the periodic table from lighter to heavier ions, the strength of the spin orbit coupling, the atomic number increases, and that's why the spin orbit coupling increases significantly. And as a result, the on-site Coulomb repulsion U and spin orbit coupling, these become competing with each other. Their energy scale become competing, and as a result, different novel quantum phases can be realized as a competition between these two competing interactions. First, let's see through this schematic phase diagram how the novel quantum phases can emerge in different region of this spin orbit coupling lambda and on-site Coulomb repulsion U. As we can see in the weak correlation regime, as the strength of the spin orbit coupling increases, a simple metal can be transformed to a semi-metal, or a band insulator can be transformed into a topological insulator. As in the weak spin orbit coupling regime, as the strength of the spin orbit on-site Coulomb repulsion increases, a metal can be transformed to a Mott insulator. Whereas if we look in the intermediate regime, where the strength of the spin orbit coupling and on-site Coulomb repulsion U is more or less similar, they are comparable. Different phases like wheel semi-metal, spin orbit assisted Mott insulator, or spin liquid or topological Mott insulator phases can be realized. This really gives a motivation to study in the bulk perovskite or the low spin bulk perovskite what are the different phases that can be realized as a function of on-site Coulomb repulsion U and spin orbit coupling. And with this motivation, we chose an AbO3 perovskite, which is a 5D transition metal oxide, is very famous strontium iridate, to see what are the phases that can be realized in this material as a prototype. This is just a prototype material as a function of U and lambda. So this strontium iridate, it stabilizes in a PBNM space group with orthorhombic crystal structure. As you can see, the octahedral tilt and rotation angle, these are very large, which means that this crystal structure is strongly distorted. First, let's see, before going to the bulk electronic structure of this system, first let's see, in the presence of strong spin orbit coupling, crystal fade and on-site Coulomb repulsion, how the d orbital is split. So in the case of isolated atoms, as we all know, the d orbital are all 5-fold degenerate, and when it comes in the crystalline environment, and then as a result of the crystalline field, the 5-fold degeneracy is split into 3-fold degenerate T2G manifold and 2-fold degenerate EG manifold. And further, with the application of spin orbit coupling, the real spin state transform into pseudo spin 3/2 and pseudo spin J half state, which are separated by a gap of 3/2 lambda, where lambda naught is the real spin orbit coupling strength in this material. And further, with the application of U, if these materials are correlated, then the upper J half band split into lower upper Hubbard band and the upper Hubbard band, which creates a band gap in the system. But in this system is very weakly correlated, as I explained in the previous slide, because the U is very weak in this system due to the extended nature of the 5D wave functions. So as a result, you can see the J3/2, because this is a D5 system, there are 5 electrons in the D state. So as a result, the 4 electrons occupy the lower J3/2 state, which are reflected here. These are the J3/2 state, which are completely occupied. And there is a half-filled J half state, which lies here. And this form a Dirac node at the high symmetric point U. So this is a Dirac semi-metal with a large spin orbit coupling strength of 0.43 electron volt. So we took this as a prototype system, and then we ask a question: what are the different phases that can be realized in these kind of systems? So first, to get an intuition, we start with a model Hamiltonian. First, we construct the tight binding model of this structure. So as I already explained in the previous slide, this structure is strongly distorted. First, we begin by creating the tight binding model for the undistorted SRAO3. So the model Hamiltonian is the following. The first term in this term represent the on-site energy. The second term is the tight binding interaction, where T is the hybridization strength of the orbital, whereas C dagger and C are the annihilation and creation orbitals, the operators. And the last term of this Hamiltonian is the spin orbit coupling, which all the terms are written in the second quantization formalism. So we make this model, and these are the DFT band structure, and you can see the model tight binding band structure are in very excellent agreement with each other. They are very nicely fitted with these as the tight binding parameters, where the energy scale is roughly 0.38 electron volt, which is roughly comparable to the spin orbit coupling strength, which is 4.43 electron volt. So after making the undistorted, the tight binding model for the undistorted structure in the basis of 2 bases, T2G and EG orbital, we then make its tight binding model in the distorted frame, because in the crystal structure I showed that this is a very strongly distorted system. So how to make the tight binding model of the distorted case? So we designed the Euler, the rotation and tilting matrix, which is compatible with the distortion of this material, the distortion of the IRO6 octahedra in this material. And using this transformation equation, where these are the matrix for the undistorted case, we get the matrix for the distorted case by using these transformation equations. And as you can see, the DFT and the tight binding structure, they are again in very well agreement with each other. As you can see, the EG state and T2G state as a result of the distortion, this octahedral distortion, they get segregated very nicely. And at the high symmetric point U, there is a Dirac node which forms, as I already shown in the bulk electronic structure. This is a Dirac semi-metal with a Dirac node at the high symmetric point U. So with model, these things are very well kept. Now, to realize what are the different quantum phases that can be realized in this system as a function of on-site Coulomb repulsion U and spin orbit coupling. So we begin with the full-fledged model, the multi-band Hubbard model. So the first term in this model is the tight binding interaction, which is already constructed, as I explained in the previous slide. The second term is the on-site Coulomb repulsion. The third term is the on-site Coulomb repulsion, but it is the intra-orbital, same site, but between different orbitals. And the third and the last term are the Hund's coupling and the spin orbit coupling. So this model we solve self-consistently in the Hartree approximation, and the results are the following. So as we can see, without a spin orbit coupling, the system shows a ferromagnetic metal phase, while as the strength of the U decreases and we put the very small spin orbit coupling strength, then the ferromagnetic phase transforms to a G-type antiferromagnetic phase. And further, as the strength of the U increases from 5T to 10T, where T is the energy scale, as I explained, it is 0.38 electron volt. The G-type AFM phase transforms to a G-type antiferromagnetic insulator phase. Whereas in the case of distortion, the ferromagnetic metal phase transforms to a ferromagnetic insulator phase due to the presence of strong distortion in the system. So this really indicates that in this kind of perovskite system, the U and lambda can lead to different type of quantum phases in the system. Then we begin to make the phase diagram, use a full-fledged phase diagram in the space of on-site Coulomb repulsion U and spin orbit coupling lambda, using the first principles DFT calculation. As you can see in the phase diagram, which is produced on this using this prototype material SRIRO3. The system shows 5 quantum phases. These are ferromagnetic metal, ferromagnetic insulator, canted antiferromagnetic insulator, canted antiferromagnetic semi-metal, and Dirac semi-metal. So as you can see in the weak correlated regime, at the strength of the spin orbit coupling increases, the ferromagnetic metal phase.
2 minutes remaining.
Transform to a Dirac semi-metal phase. Whereas in the weak spin orbit coupling regime, as the strength of the on-site Coulomb repulsion increases, the ferromagnetic metal phase increases to a transform to a ferromagnetic insulator phase. Whereas in the intermediate regime, we get a canted antiferromagnetic insulator phase. Interestingly, we can see that in this line, where the U is fixed 4 and the strength of the spin orbit coupling increases from 0 to 2 times the real spin orbit coupling. Lambda naught is the real associated strength, which is scaled as follows. So when the strength of the spin orbit coupling is roughly twice of the original, you can see all the spins aligned in plane. So there is a spin reorientation transition from z-axis to the in plane as the strength of the spin orbit coupling increases. And as you can see, there are different material which can be, there are 4D transition metals or 5D transition metal which can be realized in this phase diagram. So they are very well fitted. The downstate of this material is very well fitted to this phase diagram. Now, what is the role of structural distortion on the magnetic structure? So how the So as we can see, when we in the case of distortion, no distortion, we get all collinear phases. So the non-collinearity is gone, and we get all collinear phases. So the non-distortion transforms in all the non-collinear phases to the collinear phases. And we explain the origin of the due to the octahedral distortion. So there's all the non-collinear phases emerges due to the presence of octahedral distortion in the system. So when there is no distortion, there are all collinear phases, and when there is distortion, they just vanishes. Now, what about the low skin perovskite in the reduced dimensions? So how the magnetic phase transform when you reduce the dimensionality of the system? For this case, we designed 3 termination: symmetric IRO termination, symmetric SRO termination, and asymmetric IRO2 SO termination. For the symmetric case, we see very trivial kind of phases. So, but just one phase pops out in compared to the bulk, that is the antiferromagnetic insulator 100 phase, which is magnetic. All the moments aligned around the 100 direction. Whereas in the case of asymmetric termination, we got all the metallic phases in the phase diagram.
Sorry to interrupt, Amit.
10 seconds.
Can you conclude your talk, please?
Just 20 seconds. So we get all metallic phases. But in the case of symmetric termination, we get a very trivial, non-trivial quantum phase, which is a non-magnetic multiple Dirac state phase. We get multiple Dirac state in the vicinity of the Fermi level. And but about the magnetic anisotropy energy, so as you can see, the transition metal, multi-layers, transition metal, and oxide, they have very less magnetic anisotropy energy in oxides. But in this system, we indeed get a very large magnetic anisotropy energy, which is at least 1 to 2 order higher as compared to the conventional transition metal and transition metal oxide. And the origin of it we explained using second order perturbation theory of spin orbit coupling. So here I will summarize my talk. So we explored the novel quantum phases in the U-SOC regime. we explore how these noble quantum phases transform as a function of termination and dimension, and we estimate very large magnetic anisotropy in the interfilm films and its underlying origin. So thank you.
Thank you, Amit. Due to lack of time, we have time for one small question.
Please.
Very brief question.
Yeah.
Okay, I can ask. So, what is the significance of this work you are performing?
Yeah. So actually, the significance is that, so if you see this bulk perovskite, right? So there are very competing interaction. You have Coulomb repulsion, on-site spin orbit coupling, crystal field splitting. So there's all this competing interaction interact and they create different quantum phases in the system. So first, to answer. So in the bulk, we explore all the quantum phases that not only 5D, but all the 3D, 4D, and 5D perovskite that they can exhibit as a.
Okay. I think there is some problem from Amit's side. Yeah. So due to lack of time, we will end the talk here. Thank you very much, Amit. So we'll move to our next speaker. The final talk for this session is by Dr. Bushra Irfan from Aligarh Muslim University. Topic of this talk is magnetotransport study on magnetically doped Bi2-Se3 topological insulators. You can start your talk, please.
Yeah. Hey.
Yeah.
Yeah. So let me share the screen.
Yeah. Sure.
Yeah. Can you see the screen?
Yes. Yes. Can you make it full screen?
Okay.
Presentation mode. You can press F5.
Okay. Wait. No, it's fine.
Yeah, we can see the slide.
Hello.
Yeah. Yeah.
Is it visible?
Excellent.
Can you
Yeah,
see the full
start.
screen?
Yes. Sure.
Yeah. So can I start the talk?
Sure. Please.
Can I start?
Can you hear me?
Hello.
Yes.
Can I start the talk?
Yes. Sure.
Do you hear our voice?
I think
Hello?
she cannot. I think she
Yeah.
cannot hear.
Sorry. So can you hear me? Hello.
Yes.
Yeah, we can hear you.
Yes, we can hear you.
Yeah. Then it's fine. Thank you.
Please go
sorry
ahead.
for the disruption.
Yeah.
So I'm Dr. Bushra Irfan. So today I will going to present my result on the magnetotransport study on magnetically doped bismuth selenide topological insulators. So the outline of my presentation includes the introduction, my understanding towards the topological insulator, and why we are interested in the magnetotransport study of magnetically doped bismuth selenide topological insulators, the motivation behind the work. Then I will go to the experimental methods that we have used in studying the magnetotransport study, result and discussion, and finally the conclusion. So topological insulators are the new phase of matter. In two-dimensional system, we have a conducting edge states and we have insulating surface states, whereas for a three-dimensional system, we have conducting surface states with bulk insulating. So this data was done on our sample by one of our collaborators at PSI Switzerland. So our crystals show bulk topological insulators in bismuth selenide. So this was done by one of our collaborators. So how we can understand the topological insulator? So the easiest way to understand the topological in terms of the quantum Hall effect, or we can say that quantum Hall effect is the first example of topological insulators. So what happens in the quantum Hall system, that if you apply a strong magnetic field to a two-dimensional system, the energy levels are quantized, and these quantized energy levels are known as the Landau levels. And if the Fermi level lie in between two Landau levels, such that the Fermi level, below the Fermi level, we have filled levels, whereas above Fermi level, we have empty levels. So we can relate it similar to that of an insulator, where we have a conduction and valence band separated by energy gap. But what happens to the two-dimension state is that due to the presence of the strong magnetic field, the electron will experience a Lorentz force and form a cyclotron orbit, whereas at the edges the electron try to form the cyclotron orbit but bounces off due to the boundaries and thus move in the forward direction. Whereas these electrons on the surface, they will not take part in the conduction. Only the electrons at the edges due to boundary take part in the conduction. So thus we can say that the conduction take place at the edges and not on the surface. So this is very similar to the topological insulators of two-dimensional topological insulators. However, the drawback of this quantum Hall effect system is that it requires a magnetic field, and the idea of topological insulators spark from here by imposing a simple question, that is it possible to have a quantum Hall effect without a magnetic field? And the answer to this question is yes. If we consider a system such that if we apply a magnetic field in upward direction, then the system will have spin up electrons, and if we apply magnetic field in downward direction, the system will have spin down electrons. And if we recombine these two systems, the net magnetic field will be zero, and we are left with counter propagating spin edge state as shown in this figure. So we can say that quantum spin Hall effect is also anomalous known as topological insulators, and the role of the magnetic field in this system is played by a spin orbit coupling. So topological insulators are generally observed in a material that have high spin orbit coupling, and the conduction take place due to the spin of the electrons at the edges for a two-dimensional system. So what happens if the electrons encounter a non-magnetic impurity? So if electron encounters a non-magnetic impurity, so since it doesn't have a backward moving channel or back scattering channel, so it will just take a clockwise or an anti-clockwise turn around that impurity. And because it has the surface states are protected by a time reversal symmetry in case of non-magnetic impurity. What happens if we have a magnetic impurity? So then the time reversal symmetry is broken, and what we get is that if we dope this topological insulator with a non-magnetic impurity on the surface of the topological, so this conduction and the valence bands are separated and energy gap is introduced in this. So due to non-magnetic, so magnetic impurity opens a band gap on the surface of the topological insulators in the bulk. And this has been predicted theoretically as well as experimentally, that with doping concentration, the band gap opens, and it has been predicted both by experimental as well as the theoretical prediction that with doping concentration, this band gap opens. So with this motivation, we have also grown the magnetically doped topological insulators, and we have used the modified Bridgman technique to prepare the crystal. So in modified Bridgman technique, we have modified the shape of the ampule and placed the ampule vertically inside the furnace. Since the temperature is high at the base, so the nucleation take place and the crystal at the base, and the crystal grow along this in this direction. And the temperature time graph for the crystal growth is shown here. So first we increase the temperature to 850 degree in 24 hours, then maintain the same temperature again for 24 hours, and then cool it to 650 degree centigrade at a rate of 1 degree centigrade per hour, and then quench it in liquid nitrogen. Once it is done, the snapshot of the ampule with the crystal form is shown here. Then we break this ampule, and the snapshot of the single crystals are shown here. In order to confirm whether the cobalt is present in this, so we have wrote the single crystals of cobalt with different doping concentration, that is 0.15, 0.1, 0.15, and 0.2. And interesting feature was only observed in this highest doping of the cobalt. So we have also performed the EDAX spectrum in order to confirm whether the cobalt is present in this or not. So EDAX SWAVA spectrum shows that cobalt concentration was there in this bismuth selenide single crystals. Then we perform the magnetic measurement on cobalt doped bismuth selenide. So we can see in this that for lower doping of cobalt, there is a decrease, there is no saturation magnetization was observed. A decrease in magnetization at high field is due to this decrease in magnetization at high field is because of the diamagnetic contribution of the bismuth selenide matrix. So that's why we get this decrease in magnetization. But as we increase the cobalt concentration, we can see that we have achieved a saturation magnetization for cobalt 0.2 Bi2Se3. Also, at 2 is equal for temperature, we observe at higher temperature, we observe a diamagnetic behavior, but as we increase the temperature, we observe a paramagnetic and then to ferromagnetic with a saturation magnetization equal to 0.5 EMU per gram. And if we zoom this portion at T is equal to 2 Kelvin, we can see that we have achieved a coercive field very small, that is around approximately equal to 30 orestes. Thus, we are mainly interested in this, that is cobalt 0.2 crystals, and we have thus carried out further measurement only on these crystals. The empty measurements was also performed on these crystals in zero field cooling and field cooling. In zero field cooling, we cool the temperature with no magnetic field, then switch on the magnetic field and then cool the temperature again. We observed that below 12 Kelvin, diamagnetic behavior was observed, and the data was this zero field cooling data was fitted using an equation, that is chi0 pi naught dt plus c upon T plus theta, where the first term represents the magnetic susceptibility at 0 Kelvin, and the second term describes the diamagnetic contribution to susceptibility with D, and diamagnetic with the where D is the diamagnetic constant, and the third term represents the Curie-Weiss expression. And we can see that the experimental data is fitted well with the theoretical data, and we found that the Curie temperature, that theta is equal to plus 1.5 Kelvin. The positive value confirms the ferromagnetic contribution to the magnetic susceptibility. We performed the electrical measurements on these crystals, and since we know that for undoped bismuth selenide, that is for pure bismuth selenide, we observe a metallic behavior, right? And a similar behavior was observed for cobalt 0.5 as well. But when we did the RT measurement on cobalt 0.2, we observe increase in resistance with decreasing temperature in the lower temperature regime, that is between 0 to around 40 Kelvin. And if we plot it on logarithmic scale, we can see that there is sharp decrease in resistance with increase in resistance with decreasing temperature. And this effect is a characteristic feature of a Kondo effect, which arises due to magnetic scattering of electrons with a magnetic impurity in these crystals. So, and this data is fitted well using a Kondo model, which is given by this equation, and with a Kondo temperature around 60 Kelvin. We have also performed the magnetor resistance measurement on these crystals, and we found that there is no interesting feature was observed. Basically, we generally observe a weak anti-localization in topological insulator that arises due to quantum interfering nature of topological insulator, but we do not observe it in this cobalt 0.2 Bi2Se3 because it is a bulk crystal. Thickness is very high, and weak anti-localization effect becomes irrelevant if the thickness is greater than 100 nanometers. So that's why we do not observe any weak anti-localization features. So in order to study the surface states, we make a device by we make a device using mechanical exfoliation technique, because we are mainly interested in the surface state of these cobalt doped bismuth selenide. So we know that bismuth selenide is a layered structure and which are held together by weak van der Waals forces. So we can easily exfoliate it using a Scotch tape, and then we peel it off several times and place the Scotch tape on silicon dioxide substrate and find the desired flake that we are interested in and pattern the metal contact using electron beam lithography. So for metal contact bismuth selenide, several procedures are involved, like a spin coating of Si2 wafer with electron beam resist, then designing electrodes using
2 minutes remaining.
computer-aided design, then expose the design with electron beam lithography, and then deposit metal on it, and then lift off process has been taken. So once the devices are made, so the image of the device will be, the SEM image of the device is shown here, and we use this geometry for transport measurement. Then next, in order to confirm whether this geometry or this flake has cobalt concentration on, we again perform the EDAX spectrum, and we found that here also we can see some cobalt concentration was present, right? So next we perform the transport measurement or electric measurement on this device, and the RT curve shows metal to semiconductor transition. Here we can see that around T is equal to 40 Kelvin, there is a drop in resistance, and this is related with the, this is due to the Kondo effect that arises due to a magnetic scattering. So
Last 1 minute.
Yeah, let me, so Kondo effect is observed, and since there is a transition from metal to semiconductor, we can say that there is a band opening at the Dirac point, and this is further confirmed using a magneto-conductance curve, and we can see that there is a transition from weak anti-localization to weak localization, and it was proposed by Liu et al. The mechanism behind the transition from weak anti-localization to weak localization, basically due to a break of time reversal symmetry, and opens a band gap at the Dirac point. So this is a clear manifestation of the band opening at the Dirac point. So there are some preliminary results, which I will not go into the details. We have also grown MB bismuth selenide in MBE with the aim to study switching magnetization, but we achieve a different result. And this is a device that we have achieved. So we on the top of bismuth selenide, we have a ferromagnetic layer. So if we perform the RT measurement, we observe this semi-conducting behavior, and we also perform the magneto resistance curve. Although this is a very, I mean, like initial results, so we cannot comment more on this. So only we can say that the magnetic layer that we have deposited get doped in bismuth selenide, due to which we observe this. So finally, the conclusion: the Kondo effect that arises due to magnetic impedance well fitting using Kondo model, the bulk carrier concentration is too high. So that's why we have fabricated the device using electron beam lithography, and the signature from crossover between weak anti-localization to weak localization clearly indicates a band opening at the Dirac point. And these are the references. I would also like to thank my supervisor, Professor Ratha Chatterjee and Professor Mandar Deshmukh, and other collaborators for all the support in completing the experiment. And I would also like to thank the organizer for giving me an opportunity to present my work. And thank you.
Thank you very much, Dr. Bushra, for presenting your investigations on bismuth selenide-based topological insulators. Floor is open for 2 questions or from audience. Yeah, thank you. Any questions from audience? If not, I can ask a few questions. Yeah, so for your cobalt-based bismuth selenide, how did you verify it's a single crystal?
Yeah, so we have performed the Laver diffraction, which I have not shown. because various for when we grow pure bismuth selenide, we did all the measurements in order to confirm that it's a single crystal, and on the basis of that we have did the different doping concentration. So in our previous, we have a published paper on this, that the bismuth selenide, we have used Laue diffraction pattern to confirm, and also HRTM confirms that it's a single crystal.
Okay. Yeah. Thank you very much again. If there are no questions from audience.
May I ask a question?
Yeah, please.
So what is the value of HLN model in your material?
Yeah, so in this we have not calculated the HLN model because we are more interested if it is a pure bismuth selenide or for non-magnetic impurities we generally calculate, but here we are not interested mainly in the HLN model. We are mainly interested in the weak crossover from weak anti-localization to weak localization. So we have not calculated the HLN model and the value of alpha and alpha. We have not calculated in this for this work.
Okay, so my another question is that so weak anti-localization is not the only reason that it is topology insulator. So how is you will be confirmed that it is topology insulator?
Yeah, so basically you're right, that is but the RT behavior also shows, because for pure bismuth selenide the RT shows a metallic behavior, but here we do not observe a metallic behavior. We observe a semiconducting behavior as well. That's why first we did the RT measurement, and then we moved to the this magnetoresistance measurement. If it was a pure bismuth selenide, then we will get a metallic behavior.
Sorry to interrupt. Time for this session has ended. So thank you again to all the speakers, and more importantly to the audience to be excited until this time and with their thoughtful questions. Yeah, so this session is ended now. Thank you very much.
Okay, thank you.
Yeah, so we will meet after 2 o'clock in the afternoon. Yeah. See you all. Bye.
See you.